Well, okay. So we've talked a little bit about antiderivatives, right? And now we're actually going to solve some problems that have derivatives in them. And we need to solve for the function. The only way to do that is going to be to take the antiderivative. So let's take a look at this problem here. We've got y prime minus y sine x equals 0. The objective here is to solve for y in terms of x. So in other words, I need to make this look like a y equals problem that you would encounter in pre-calculus. So how do we do that? Well, there's one main step we do, and then everything else is going to flow from it. Let's take a look at what that step is. It's called separate the variables. Now, we're going to talk a lot more about this as we solve more of these problems in the future, but this is your key step. So let's replace the y prime with a dy dx minus y sine x equals 0. So you can see here that we have y's and x's. And the good thing for you in this introductory calculus course is that we're only going to be dealing with two variables. And they're all going to be fairly straightforward when it comes to solving for them. So what we need to do here, separate the variables. Let's get the y's on one side and the x's on one side. How will we do that? Dy dx equals y sine x. Okay, that's closer. Now I've got this x here and this y here. Can we do something about that? Yes, we can. Dy over y equals sine x dx. Okay, now we're ready to take the antiderivative. And the reason I chose this one is because this is one of the more tricky antiderivatives. And I know what you're thinking. Don't all teachers just choose the easy example and then give us the hard ones for homework? Most of the time that's true, but not now. So today we're going to take a look at this tricky one. Now, what you got to think about is, what are the functions whose derivatives are here? Now, we use the symbol of the integral when we mean to take the antiderivatives. But we don't even need to do that now because we haven't really learned all of that yet. We're just going to think about this as the antiderivatives. So let's rewrite this last step as 1 over y dy equals sine x dx. Okay, and here's how you think about it. What is the function whose derivative is 1 over y? What is the function whose derivative is 1 over y? On my planet, that is the natural log of the absolute value of y. Is that true? That's right, 1 over y. Now, how about the function whose derivative is sine x? Let's see, the derivative of cosine is negative sine, so the derivative of negative cosine would be sine. And then remember, we always have the c. And now I know what you're thinking. What happened to the dy and the dx? Well, when we take the antiderivative, they go away. Just like when we took a derivative, they appeared. Do you remember that? Do you remember when we had y equals 3x squared plus 7x, and you said, okay, let's take the derivative, that's dy dx equals 6x plus 7. Do you remember doing that? Right? That became the derivative. When we go the other way, these two things go away. Okay? Now, we're still not done yet here, although we're done with the calculus. Now, if you take this into any advanced algebra kid, they should be able to solve this for you Because what would they do? They'd say, natural log of something equals something. That means the absolute value of y equals e to the negative cos x plus c. Now, can e to the anything ever be negative? If you said no, you would be correct. So we can get rid of the absolute values. So y equals e to the negative cos x plus c. Now, this is done. This would be full credit. But let me show you a little trick that was often employed in calculus, solving these problems. All right, so what happens is, remember your exponent rules? When we add the exponents, we were really multiplying the bases, weren't we? And so that e to the c becomes a new constant, right? Because that's just a constant to a constant. So we'll call that a, e to the negative cos x. And then at this point, if we had an initial condition, we would plug it in. But since we don't, I'm very happy with that solution right there. Okay? So I want you to remember this and write this down, because this is going to be one of the most common separable differential equation problems that we do in this course. And it stems from this idea here, having to use the natural log. Okay? This occurs frequently. It's good to have in your notes. It's good to see it now so that when we see it again in a month or two, you'll be like, oh yeah, I kind of remember doing something like that. So make sure you can get this down. And this is how we begin to separate the variables in solving our differential equations. Good luck. See you next time.